There's a lecture schedule for the rest of the term. So today there will be a lecture. On Monday, quiz 2 will come back. I'll tell you about the exam. Maybe we'll look at some old exam questions. Wednesday there's no lecture. Monday is the overflow day. So there's 12 weeks in an Ontario University course. For some reason there's 13 Monday lectures, which is unusual, but there is no Monday lecture on the 10th. All right, topic of today's lecture is processes. So when you run a command in bash, and the command is not one of the bash built-ins, so it's not something like print working directory or something like that, what actually happens is another program runs. And so a program on a Unix-like system is made up of one or more processes. So you think of a process as being a running program, and all of the additional information that you need to manage that program. So this includes the memory that the program needs. The extra stuff, this additional information that you need to manage the program, that's something that they'll tell you about if you take an operating systems course. So Linux keeps track, or all Unixes keep track of the state of each process, and they keep them separated from all other processes. So that means in theory, because the memory between two processes is not shared, and a process is not supposed to be allowed to access memory outside of the process, that means in theory, one process can't bring down your entire operating system. Most Unixes are pretty good at that. Mac is pretty good at that. Windows used to be really terrible at it, but it's gotten better as the years have gone on. So processes can't interact directly with one another, right? So if you're running one program, there's no easy way for it to interact with another program at the same time. There are a limited number of secure operating system mechanisms that you can use to communicate between two processes. So it's most of the time one process can't crash another process or take down your entire operating system, although it does occasionally happen. All right, so when you run a program in your shell, typically it runs as what's called a foreground process, right? And so what happens is your shell gives control to the process. Right? And so your terminal appears to be unresponsive, right? Your terminal waits for the running process to finish before the terminal can respond to other commands. Now, we didn't see that a lot in this course because all of you on Windows, you can't really run any of the graphical user interface programs. So we never made a long-lived process, right? So a program that ran for a long amount of time. If you want to, you can interrupt or terminate a foreground process by pressing Control-C. Right? And so what this actually does is it sends what's called an interrupt to the process. So the interrupt's name is SIGINT. So SIG is short for signal, int is interrupt. Right? And you can stop a foreground process by pressing Control-Z. And that sends the signal SIG stop to the process. You can also run a process in the background, and we never did this either. I think I showed you once how to do this, but that's it. So if you want to run a long-lived program in the background, and you want to be able to use your shell again, then you run the program and you put the ampersand at the end of the command. Right? And so that launches a subshell that runs your program. Does it launch a subshell? Anyway, your program runs it in the background. Your terminal stays in the foreground. So your program starts up, and then you can use the terminal again. Right? And you can move processes between the background and foreground using the commands FG and BG. Right? Oh, sorry. All right, so Linux and pretty much every other modern desktop operating system is what's called a multiprocessing operating system. Right? And so what that means is, so on most computers you have one processor. Right? So your processor is a finite resource. Right? If you actually look on a running operating system, so if you ever look at Windows Task Manager, or if you know how to access Mac's process manager, and you look at how many processes are running on your computer at any one time, it's a lot. Right? So if I just start up Task Manager on my computer here, right, you can see there's a bunch of programs that are running here, but then there's another 125 processes running in the background. Right? Each one of these processes needs the CPU and other system resources. Right? And so if you only have one CPU, the question is well, how are all these programs seemingly running at the same time? Right? And that's the big illusion that a modern operating system provides. Right? So a modern operating system takes your CPU and divvies up time on the CPU to each process. Right? So in the Unixes, the goal is to have one process always running on the CPU at all times. Right? So in order to maximize this limited resource. Now, obviously, as I just showed you, there's way more processes than there are CPUs, right? So even if you have a multi-core CPU, it's almost always the case that there's more processes running than there are cores. Whoa, sorry. And so the operating system needs to schedule each process so that it gets a amount of time on the CPU. Right? So assume you just have one CPU, you have many processes, right? Then the way the scheduler works is it gives time to one process, right? And then it stops the process. Then it gives the CPU to another process, stops that process, gives time to the next process, and so on and so on and so forth. Right? And this happens so quickly that you can't, usually you can't tell that your processes are not all running at the same time. Right? They run for a short amount of time, then they wait, then they run for a short amount of time, and they wait, and so on and so on and so on. Right? All right, so the reason why this happens is because, so number one, there's lots of processes, they all need CPU time. And number two, often when a process is running, it doesn't actually need the CPU. And so here's a little table that shows you some relative times. This is from about a decade ago. So the table is still sort of relevant. Well, it's still relevant. So it shows you what happened. It shows you some times for each one of these tasks, right? So your processor cycle, that's the speed at which your CPU actually runs, right? And so here we've got a 3 gigahertz processor, right? So 3 billion times per second, your CPU can perform one operation, right? I guess that's about the speed of a cell phone CPU now. Desktop CPUs reach about 5 or 6 gigahertz now. Okay, so that's one tick. So that's one tick of your CPU clock, right? It can do one thing, so one atomic operation. So something like adding 2 integers it can do in that amount of time, right? Just to access memory, so in order, if you need to read a variable somewhere from memory, right? It takes somewhere between, well, this is back in 2013. It takes somewhere between 50 and 150 nanoseconds, right? So if we scale all these times, so if we make this time equal to 1 second, right, then just to go and read something from memory, that would be the equivalent of waiting 2.5 to 7.5 minutes, right? So just to read something from memory, your process has to wait, right? Many clock cycles, CPU clock cycles, in order to get that value, right? So while that process is waiting, it would be nice if you gave the CPU to some other process and let it run. A context switch, well, at least in theory. So here, a context switch is the amount of time it takes your operating system to stop one process from running and then start another process running. Right? So that's roughly 3.5 microseconds. That's like 3.5 hours. Right? So again, if your CPU can do one operation per second, right, to swap out one process for another, you would have to wait 3.5 hours for that to take place. Right? If you are in the unfortunate situation where you still have a physical hard drive that spins, so it's got an actual platter that spins, right? For that disk to spin once, takes 8.3 milliseconds, which is the equivalent of almost a year of time on your CPU, right? So that's just waiting for the CPU to spin around once so that you can maybe read something on that on the disk. right? And finally, so this thing here called the time slice quantum, this is the amount of time in Linux that, that's the maximum amount of time that each process is allowed to run. Right, so each process is given a maximum of 100 milliseconds of CPU time in one chunk, right, which is the equivalent of 9.5 years. Right, and so you can see that if you have a process, or sorry, if you have a process that's trying to read or write to the disk, right, a lot of the time it's not doing anything, right? It's just sitting there waiting for the read or write operation to complete. So to maximize the CPU utilization, it's useful to swap processes in and out from the processor. Right? So notice that it takes a long time to do a context switch, right? But it takes a lot longer to try to read something off your disk. Okay, so a process can be in one of 4 states, at least in Unix anyway. So it can be running, so it's on the CPU doing something. Right? It can be waiting. So waiting is, the process is waiting for some event or resource, right? It can be stopped, right? So the operating system scheduler can stop a process, right? So that's what happens when it swaps the process out for another one, right? And then it can be a zombie process. So a zombie process is a process that is supposed to be dead, so it's finished. But for some reason, the operating system still is keeping track of that process. Right, so the way the operating system works is that it keeps a list of processes that are running. Sometimes that list isn't cleaned up properly when a process goes away. So you end up with what's called a zombie process. Okay, so the process manager can stop a process under many different circumstances. Right, so if a process finishes, so your program finishes running, then obviously the operating system will stop the process. Right, so the operating system does whatever it needs to clean up after the process. Right, in particular, it gets back its ID number, which it can then reuse for another process. A process will stop if it puts itself to sleep. So there's a standard function in Unix called sleep that a process can use in order to stop itself for some amount of time. Right. If the process is waiting for something to complete, then the process manager can stop it. Right? So for example, if it's waiting for input or output, the process manager can pause it and give time to some other process. Right? Now, it's not surprising that processes have the operating system keeps track of processes in terms of their priority. So some processes are much more important than others for your operating system. And so what's actually happens is that your processes are kept in a priority queue. And so if a higher priority process needs to run, it can bump your process from the CPU. Right? That's an operating systems topic. So that would be CISC220 here. And finally, if your process runs for its entire time quantum, so it runs for 100 milliseconds on Linux, it stops. Right? So the process manager stops it, gives time to another process. Okay, so here's the example of the sleep function. Right? So sleep is defined in the header file uni standard. So these are the standard Unix system calls. Many of them are defined in that header file. Sleep takes in a number of seconds for which to sleep. So when this program runs, it prints going to sleep. It then waits 10 seconds. While it's waiting, some other processes can run. Right? And then it says, I'm awake. Right? And so if you run this little program, it's not the most exciting program. Sorry, this is going to be really awkward because I have to hold this mic. And now that's going to make a big noise on the recording. Okay. So sleep. Not the, oh, sorry, wrong. Not the most exciting program. It's just going to run for 10 seconds. Sorry, it's going to run for 10 seconds and then come back. Right? If you want to run this in the background, you can do sleep, oh, sorry, Control C to kill it. So sleep and then ampersand, right? And now I have my terminal back. So that's what running in the background does, right? I can bring it to the foreground using FG, and so now it's running in the foreground again, and I don't have control over my terminal anymore, right? And now it's awake again, right? So there's an example of using sleep. We're going to use it again for some of the other examples here because it's the easiest way for me to suspend a process. All right, so the way everything works in Unix is that every process gets an ID, right? So it's an integer value that the operating system assigns to each process, right? And in Unix, every process has a parent process, right? So a process that started it. Now, of course, this all has to start somewhere. So somewhere there has to be a process that has no parent, right? And so that process on at least my Linux is called init. Mac uses something called launchd. I'm not sure if every Linux uses init or not. But it's called init. So it has a process ID of 1. It's the first process that starts when the operating system boots, right? And so it's the process that starts every other process. The command ps will list active processes if you want to use it. Again, this is really awkward. And again, big noise on the recording. ps. Right. So ps produces a list of the processes that are currently running. Right. So there you can see the process with ID number 1 is init. So that's the process that started running when I opened up Ubuntu. And then you can see there's bash, so that's my shell, right? And there's the ps command itself, right? Which so it shows itself as running when you type ps, right? TTY is the terminal in which the commands are running in, right? So this terminal is PTS0, that's just its ID, right? So my shell is running in this terminal, and PS is running in the shell, so it's also running in this terminal. If there's a question mark, then it's not running in a terminal at all. It's running somewhere else. PS tree is useful too if you want to. So PS tree shows a tree-like picture of your processes. So it shows you that init, so that's process number 1. It started, I'm not sure which one of these two inits it started. So I don't remember if it's, well, I guess these two are these two here. Then you can see init called itself twice before starting bash, bash called ps tree. Right, so it's showing you the relationship between the child processes and their parents. All right, so sometimes, although less frequently now, sometimes you have to manually kill a process. Right? So the command kill or send some other signal to a process. So kill is a very, very primitive way to send some information to a process. So what kill does, I'm not sure why it's called kill, because it doesn't necessarily stop a process. So kill sends a signal to a process. Right? Now signaling is probably, I guess it's the most primitive way that you can communicate with a process. Right? So kill sends a signal. A signal is a message that you can send to a running process. For this signaling process, that message communicates basically almost very, very little information. Right? Essentially, you can send what amounts to an integer value to the process. Right? So if you use kill minus L, you can see the available signals that you can send to a process. And if you type man7 signal, you can see what the individual signals mean. So let's take a look at that. So kill minus L. Right, and so you can see there's 64 signals here, at least on my version of Linux. Right? I believe, and notice their names are not very descriptive. Right? So for example, everything after 35 and so on just has a number after it. Right? And then man7 signal tells you what each one of these things is supposed to mean. Somewhere. Here we go. Right, and so you can see this sig abort sends the abort signal, right? And if you do man abort, you can see what that does. Where is sigint is the interrupt sig? Sorry, I'm looking for. Where's the one I'm looking for? Sig. Oh, sig stop. So there it is. So sig stop. So that one is if you type control C at the terminal, that signal is sent to your process. Right. Okay, so when you send a signal to the process, your process is allowed to handle it. So I don't think we're going to get to it, but it's possible to write some code in your process where that code handles any signals that are sent to it so that it can respond. Right? A process does not have to respond to a signal. Right? Okay, so if you just type in kill on its own, it sends CISC220 by default, right? Which will normally stop a program. However, or a process, sorry. But if your process is unresponsive, you might have to send CISC2kill. Right? Now remember, processes respond to signals, so it's the responsibility of the process to look at the signals that it's receiving and respond to them. CISC2kill is special. So CISC2kill is the process that is the signal that you send to really kill a process. Right? And so CISC2kill goes to the operating system. That's kill -9. So if you ever see K9 or something like that on the internet, it means you're trying to send the kill signal to a process. Right? So kill -9, that signal goes to the operating system. The operating system is then responsible for stopping the process. Okay, so if you have a program, so you have a process that's running, right? Can you use that program to start another process, right? So the shell does that, for example, right? You type something into the shell, it launches a command, right? So the shell is a process that's capable of launching other processes, right? And so the question is if you're writing your own program and you want to start another process, how can you do it? So by far the simplest way to do it is with the system call. You should generally avoid this. It's not secure, right? But if you're playing around on your own computer, it's fine, right? But you don't want to do this sort of thing in production software. So the way system works is you pass it a command that's encoded in a string, right? And then the operating system will call a shell to process that. Sorry, not necessarily a shell, a command processor to process that command. Right, so for example, I can write a little C program that launches another program that's on the path. Like so, right? So I can write a little C program. It uses the system call to launch the program go to sleep, right? So this works as long as go to sleep is in the current directory, right? So that's why the / is here, right? So let's take a look at this. So go to sleep is right there, right? And if we look at go to sleep, right? So all go to sleep does is sleep for 10 seconds, right? So I'm going to write a program that calls the go to sleep program, right? So that's, oh, sorry. Whoops, sorry. Oh, wait, sorry, wrong one, sorry. Cat system. Right, and so there's a version of the program that actually prints out what it's doing. So when we run it, right, so it calls the go to sleep program, which goes to sleep for 10 seconds, and then while we wait for it for just a second, when it wakes up, it prints out there it is, it prints out I'm awake, and now our other program stops. Right, so that's kind of neat. You can write a program that starts another program. Right. So in Linux, system starts another shell. So it launches the shell and then runs the command in that shell. Right? Now, this is dangerous to do if the command that you're running, if you're not in control of the actual command that's running. Right? So for example, it just takes in a string that includes the command to run, right? That string also includes any arguments you want to pass to the program, right? If you get this string from some unknown user, right? So for example, if you ask them to type in something at the command prompt, they can launch any process that they want, right? That you have permission to run. So if you click on this link here, sorry, just a second. It takes you to this page here. Right? Notice the title. The title is "Do not call system." Right? So it tries to warn you this is not secure. Right? And so it tells you why it's not secure when you pass in an unsanitized or improperly sanitized command. So when you pass in a string that you haven't validated, right, system will just run whatever command is embedded in that string. So they give you a little example of what happens when you use system. It gives you an example of using system and what can happen if you don't, if you're not careful about the inputs that you pass to it. So here's a function, right? It takes in a string, right? That string gets, where is it? System, where's the system? Here. Okay, so that string gets attached to, the function takes this printf and it takes the command, it prints the string any command into the buffer, and then it takes the string that you passed in, puts it in single quotes, and attaches it to the end of any command, right? And so that's the, that's the command that gets passed to command, that gets printed into command buffer, right? And then command buffer is passed to system, right? So notice that it single quotes the string that you pass to the function, right? So if you pass it this string, right, then what ends up happening is, right, when you run snprintf, you get any command, right? So you get any command, right, followed by happy, right? So assuming that was everything that was there, when you ran system, it would run that command passing in the command line argument happy, right? But because there's extra stuff here, right, we end up with, the single quote. So up, back here there's a single quote, right? And then the string that you passed in. So we passed in happy, single quote, semicolon, user add, semicolon, single quote attacker. Right, and then there's a closing single quote over here. Right, and so system launches this command, all of that. Right, so it launches the command, any command passing in the string happy. Remember, semicolon, that's the, what exactly is that called again? That's the command separator in Bash, right? So then it runs the command user add attacker, right? User add is the command that you use to add a new user to your system. So if whoever's running that has root access, then you end up adding the user attacker to your system, right? And so, system is extremely unsafe unless you properly validate the input to the function, right? Anything else here? Oh, so it says instead of using system, you should use that function right there. But that's actually a whole family of functions, which we're probably not going to get to in this lecture. Okay, so every process gets an integer ID when it's created. The ID is unique for the lifetime of the process. But once the process is done, the operating system is allowed to recycle the ID. Now, the way the Unixes work is that the number of IDs is finite. So you can only launch a limited number of processes before the operating system runs out of IDs. The function get PID, PID is the, PID is get process ID. So that returns the ID of the current running process. Right. It's just an integer value. Right. Get PPID is get the parent process parent ID. Right. So the ID of the parent process. Right, which also returns an int. Right. So here's our program. This one is go to sleep n. Right, so this one goes to sleep for n seconds. When it runs, it tells you what its process ID is, so it uses get PID here to get its ID. I think the version that I'm actually going to run also gets the parent ID. So it prints out the process and the parent's ID when you run it. Oops, sorry. Alt tab. Okay. So this is go to n seconds. So we'll sleep for 2 seconds. 3 seconds. 2 seconds. Right. So it says that go to sleep n. Its process ID is 212. Right. The parent ID that the process ID of the process that launched it is 9. If you do PS, right, you can see that 9 process ID is my shell. Right. So you can see that the process that launched go to sleep n is just the shell that I typed into. Okay, so execv and there's a whole bunch of these. So there's execv and a whole bunch of variations of execv. All of these functions executes a process, but the way it does it is a bit funny. So it reads in a file, and it interprets the file as what's called a process image. So in other words, it interprets the file as though it were a program that you can run. The way it works is very unusual. So what it does is it takes the process that you want to run and it substitutes it for the process that's currently running. So it takes it replaces the currently running process with this process image. Right? So that's very weird. So I start up a process, right? So I'm running a program. Inside that program, I decide to launch another process. Right? If you use execv, what ends up happening is that new process basically replaces the one that's currently running, which seems like an unusual thing to do. But that's the way that it works. Right? Okay, so the way that you call it is you pass in the name of the file that corresponds to the program that you want to run. Right? And then you pass in an array of arguments. Right? So the array of arguments, these are the same, the way this is supposed to work is that you're supposed to pass in, let me just skip over that slide. You're supposed to pass in an array of strings that are similar to what a C main function would see. Right? So in argv0 is supposed to be the name of the program. Right? argv1, that's the first command line argument to the program that you want to run. argv2 is the second command line argument of the process you want to run, and so on and so on and so forth. Right? So these command line arguments are passed to the process that you're trying to launch. Right? And so here we've got execv down here. Right? So the way that you launch execv, so the way you call execv is you pass in the name of the program that you want to run. So I'm going to launch go to sleep for n seconds. Right? And then you pass in the arguments to the program in this array here. Right? So the first argument, that's the name of the program, so let's go to sleep n. The second argument, I only need 1, because go to sleep n only takes 1 argument, so I'm going to pass in 5. Right? And then this list here is supposed to be, the last element of that array is supposed to be null. Right? And so you put in a null so that execv knows how long, or knows how many strings are in this array. Right? So notice that execv doesn't take in the number of arguments. So instead, it relies on you to insert a null value into the array to indicate that that's the end of the input arguments. Right? And so if you run this one, so I just have to remember what this is called. This is execv demo. Yep. Right, so it launches process. So process 220 is uses execv. Right. So now remember what execv does, right? So it replaces itself. Execv replaces the current running process with the new process. Right. And so when go to sleep runs, it becomes process 220. Right. So remember, go to sleep n prints out its process ID. Right. So it prints out the same process ID that our other program printed out. Right? And so go to sleep n, the contents of that program replaces the contents of execv demo. right? So that's not normally the way you use exec-v, because if it was, it's kind of useless, right? You're going to write a program that launches another program, but that other program just replaces the program that you started with to begin with. So that doesn't make any sense. So normally, the way you use exec-v is you call another function first, right? So first, you call the function fork. So fork in Unix creates a new process, right? And then inside the new process, you call exec-v, right? So you make a new process. It turns out that when you call fork, fork produces a copy of the current running process. Then you replace the contents of the copy with the new process that you want. Right, okay, so this is, it's a very powerful concept, and any non-significant program that has to launch other processes on Unix anyway, is probably using fork or something related to fork. Right, so your web browser, every time you open up a new tab, is probably forking another process to launch the new tab. Right, so it's powerful, but it's dangerous. Every time you fork a process, you create another process. Remember, there's a limited number of processes that can be running at any one time. So it's very easy it's very easy to maliciously, recursively call fork, right? Or repeatedly call fork until there's no more process IDs left, and then your operating system can't start any new processes. So let me just show you what an example of that. And then maybe we'll call that quits for today. So there's something called a fork bomb. Right, which you can Google here. Right, so a fork bomb is basically a program that repeatedly calls fork until there are no more process IDs left. So you may have seen this as a meme, as an internet meme, right? If you ever see someone wearing a shirt with that on it, right, that is a fork bomb. And you might think, so that's actually, don't type this into bash. You can actually type that into bash and fork bomb your system, right? So this is very weird. So this doesn't look like legal bash, but it turns out it is. So in bash, you're allowed to use the colon as the name of a function. Don't ask me why. I don't know, right? So it's very strange. So this is defining a function whose name is colon, right? All the function does is call itself, right? If that succeeds, it calls itself again in the background, right? So in the background, it calls itself, right? When it calls itself, it calls itself again, launches another process, and calls itself in the background, right? And so on and so on and so forth. So that's your function. Whoa, sorry. Where'd it go? So there is your function definition, right? There, the semicolon is your command separator. And so the colon, this now launches the function that you just defined, right? If you replace the colon with the word fork or any other word that you want, that's the program that ends up running, right? And so you can see it just recursively calls itself, launching a new process every time, right? So in your shell, every time you call a function or launch something in the background, which is what's happening there, right? That process runs in the background, right? So it launches a subshell, which then calls and that subshell runs this function again. Right. So this recursively calls itself and never stops. On a modern Unix or on a modern Linux, this may no longer bring your system to a halt. It certainly used to. But modern operating system, or modern Linuxes and Unixes put some measures into place to prevent this sort of thing from bringing your system to a halt. Right. If you do this and it does bring your system to a halt, just reboot close. If you're on Windows subsystem for Linux, just close Ubuntu or whatever it is you're running. I don't think it'll kill a Mac, but if it does, just reboot your computer and everything will be fine. Right. Okay, so let me just go through this slide here and then we'll call it quits. All right, so what fork does is it copies the current process. Right? So whatever program is running, it makes a copy of that process. Right? So in other words, all the memory that that process has gets copied, and you end up with a second independent process. Right? The process that called fork is the parent. Right? The forked process is the child. Right? Both processes run in separate memory spaces, right? But the child is a copy of the parent. Right? The interesting thing about this is that when you fork a process in Unix, because all the memory is copied, the file streams are all copied. Right? So your standard in, standard out, and standard error of the parent are the same standard in, standard out, and standard error of the child. So that's one way that a parent and child can communicate. They end up sharing the same inputs and standard streams in both systems. In both processes. Right? And so when you call fork, the parent process continues running after the fork, and the child process starts running once fork returns. Right. All right, so here's a little demo program here that you can run or type in and run. There's a few others too, so there are more slides, but we're out of time for today, and I think that's enough for the purposes of this lecture. All right, so I guess just to, once again to remind you, that's basically the last content lecture of the year. On Monday, hopefully, I'll have quiz 2 for you, and I'll tell you about the exam, and that will wrap up the course. All right, so everybody have a good weekend, and I will see you hopefully on Monday.